Thank you for being here. Today we are going to talk about this consensus protocol called Sassafras. Yeah, who I am? I am Davide Galassi, and I am a Rust core engineer at Parity Technologies. And mostly I am working on the Sub0 framework on the SDK node team. And yeah, for this year, I was mostly focused on the Sassafras protocol implementation. Yeah, first, a short introduction about what is actually a consensus protocol and for what it's used for. As you know, the blockchain systems are just distributed systems that are composed by multiple participants to the network. And those participants actually should reach the consensus of who is in charge of producing the next block in the network. So we have to find out how those participants are reaching the consensus of who is able to claim a slot to produce the next block. Where a block is, let's say a block is the unit of computation of this blockchain system, composed by several transactions. So today the agenda is divided by 4. First I'm going to introduce what is block authoring. Then I'm going to talk about what are the problems with the current most used block authoring algorithms provided by Sub0, that is Aura and Babe. Babe is currently used by Polkadot anyway. Then I'm going to introduce Sassafras and the solution to the problems that those two protocols have. And yeah, and finally, the implementation status of the protocol itself. When I'm talking about authoring protocols, actually, with Sub0, we are mostly use what are called slot-based authoring protocols. Slot-based authoring protocols are dividing the timeline. So the timeline is partitioned in slots, and a node can actually author a block only for the slots that he's able to claim according to the consensus algorithm. So different algorithms actually have different ways to claim slots, and this is embedded in their rules. Here in the picture you can see, for example, we have two authors, one red and one green. And there are some slots that are not claimed at all, because, for example, this consensus protocol that has been used, in the end, given as a result that nobody was able to claim that slot. So the authoring protocols that we are talking about are mostly assume that there is a fixed set of authorities. So, and the timeline is divided in epochs, what are called epochs, where each epoch is a set of slots. Usually, on each epoch, we are going to announce what are the parameters to be used in the epoch that will follow. So here, for example, you can see that there are epoch n and epoch n plus 1, and during epoch n, we announce what will be the authority set of the next epoch, and some other parameters that are configurable. For example, the slot duration and others, stuff that is more specific for each consensus protocol that we are using. So what can generally go wrong in a distributed system, let's say. So first thing is that the network is unreliable, and faults usually happens. There are unbounded delays for computations and communications that are not predictable. Local clocks of the participants are not synchronized, so we cannot assume that everyone will be aware of a global clock that doesn't exist. There are also malicious or buggy behaviors, or what are called Byzantine behaviors. And we cannot do nothing about those four first issues that can arise, but we can do something about the last point, that some consensus protocols have intrinsic shortcomings that can be fixed somehow or can be improved. And it's very important to say that the consensus protocols that we are talking about are the protocols that take care of block authoring, so block productions, that are different, at least in our architecture, are separated from the protocol that is used to finalize the state of the chain. In our case, it's Grandpa protocol. And block authoring protocols favors availability, or also called liveness over consistency, also called safety. So in those protocols, we should continue to evolve the state of the chain, even though this happens while there are faults or the network is partitioned. So there can be a subset of the nodes that progress in some way, and another subset that progress in some other ways. So this will produce, in the end, two different or multiple histories of the chain, also called forks, that will emerge at some point. So those forks happens for motivations that are out of our control. And what will happen is that at some point we have to find out what is the canonical state of the chain. And every protocol actually have different ways to decide what is the canonical state to follow. So if I am the next block producer and I see that the current status of the network is that is partitioned, so there are multiple forks, I will have to decide over which one I want to produce the next block. Each protocol have different ways to decide, and this is what is called fork choice rule. This is a pluggable mechanism that actually can be plugged over all the protocols that we provide. But what it means is, more importantly, is that more forks means less throughput, because actually those forks should be resolved and should be pruned. Whoever submitted transactions in the fork that in the end was stale should resubmit the transactions. And so we want to avoid the forks whenever it's possible. So let's see first what Aura protocol is about. Is the simpler one. So the Aura idea is that the slots are assigned using a very simple round-robin mechanism. So let's say that there are two authorities, and they are ordered in a set. And who is the next authority is determined by this modulo operation. So modulo 2, so the first one will be 0, the next 1, and then 0 again, etc. What is the problem here is that it's completely deterministic, and an attacker can potentially DOS who is the next block author, preventing him for producing, or at least to spread the block that has been produced, and this will cause forks. So the forks here are not for some distributed, well-known distributed problem, but is because of the protocol that has been used. So the next attempt will be Babe, and Babe tries to address this DOS issue by using a lottery system. So for each slot, one authority uses this what is called the VRF output. The VRF is just a function that produces a ticket given some input that can be on chain, and the one input of this VRF is also the private key of the author. And very roughly, you can think about the VRF as a digital signature with a difference that, for example, for an elliptic curve digital signature, you can have multiple signatures for the same input, while with VRF not. The output will always be the same for the same input. And so according to the output of this VRF, if the output is below some threshold that is configurable and on-chain and known to everybody, I have the right to claim a slot if my output is below this threshold that is on-chain. And if I can produce a slot, I will produce it, and I will reveal my ticket and my authority only at the time of the block is produced, so nobody can actually DOS me. Oops. So the idea is also the Babe weakness, because this lazy disclosure can allow to have several authorities that can claim the same slot. So because multiple authorities can have their output of VRF below the threshold that is registered on chain, so multiple blocks from different authors will be produced for the same slot per the algorithm. So it's not some kind of fault. It's just an intrinsic problem of how the algorithm is actually designed. So let's talk about Sassafras. So in Sassafras, actually, we have where each slot can be claimed at most by one authority as Aura. And also, the slot assignment is not disclosed until the block production, as for Babe. How this is possible? Actually, the solution to this problem is to use this thing known as zero-knowledge proofs. So the next epoch authorities submit a bunch of candidate tickets in the attempt to reserve slots for the next epoch. The tickets are registered on chain and are organized. So once that the tickets are registered on chain, those tickets are organized in such a way that will be only one ticket per slot reserved by someone that at the moment of the submission of the ticket is not known who is, but we can check that actually the ticket has been produced by a valid authority. So this zero-knowledge property allows, when we submit the ticket is submitted along with a commitment proof attached to each ticket. And everyone can, at that point, can check that the ticket has been produced by one of the authorities registered for the next epoch without actually know who is the creator of that ticket. So at the point of registration of the ticket, the authority that submits it is secret and is disclosed later, only when the ticket will be claimed. So the ticket will lazily disclose their identity only on block production, and ownership at that point is claimed using a different proof, not the one used on block submission, but another proof. So the ticket production, so what is the input for this VRF used for ticket production? Let's say that, simplifying a bit, the input for to produce the ticket usually is some kind of epoch randomness, so a value registered on chain, shared by everyone, so everyone can eventually use it on verification of the ticket, and the attempt number. As I said, the authorities, when they submit the tickets, they are not submitting only one ticket to claim one slot in the next epoch, but they will submit a bunch of tickets, and only the tickets below a threshold that is on chain as well, they will be considered valid tickets. And yeah, technically, the ticket proof that is attached to the output of the ring VRF is built using this primitive called ZK snarks, where snark means succinct non-interactive argument of knowledge, and is a pretty bleeding-edge cryptographic primitive. I think that they first used on blockchain on 2012, if I'm not wrong. And yeah, in cryptography, this is pretty bleeding edge stuff. And we, as implementers, we don't need to actually understand or know everything about the cryptographic back end of this primitive, but we just use the services that it provides. The submission of the tickets that are produced by an author can be direct, meaning that the author can directly submit the tickets on chain via a transaction. This is obviously not super anonymous because actually someone can track who is the producer of the ticket and then check who actually submitted it. But this is the way that the current status of the implementation is using. This is fairly temporary. In the next iteration of the implementation, we are going to use proxies and mixed-net networks, where, for example, Alice will encrypt the tickets using the mixed nodes public keys, and then the mixed nodes will hide the origin of the ticket producer before reaching the last mixed node that will submit it on chain without even knowing who was the original producer. And yeah, the ticket submission, well, there are some constraints with respect to the ticket submission. The submission can happen only in the first half of the current epoch. This is to allow the system to actually stabilize, and eventually, if we are using a finalization protocol to finalize the state before the next epoch starts, and so to not just start with a fork immediately, so that at the point that the next epoch starts, the state is pretty stable and everyone will have hopefully the same view of the network. Then on submission, also the tickets threshold is checked, and then zero proof is checked before actually finalize, store it on chain. Next, the tickets, we can receive more tickets than the slots that are composing an epoch. What happens is that if we are receiving more tickets than slots, we are pruning the tickets with the bigger values. And yeah, what will be left, it will be assigned, the tickets will be assigned to the epoch using this assignment called outside-in order. You can see the assignment here in this picture very well. So this is to actually hide somehow what your ticket will be, to what slot your ticket will be assigned to as an author. So not everything is perfect, and what can go wrong with this new protocol. So this is something that can be solved. So what happens if less tickets than slots are submitted on chain? If less tickets than slots are submitted on chain, the middle of the epoch will not be covered by any ticket at all. And in that case, the middle of the epoch will be covered using a fallback assignment that is very similar to Aura that we just saw. So there will be some predictable fallback mechanism that will kick in to cover. And this is the strategy that is also used on Genesis as well. Because you can see the Genesis as an epoch where we don't have any ticket yet on chain and will be covered by this fallback mechanism. And another thing that can go wrong is that the ticket is not claimed at all by any authority that previously registered the ticket on chain. This is a problem because the ticket production for that slot will be skipped. So the throughput is affected. The author of but the author identity is not known, so no punishment is possible at all. But me as an author, I don't have any reason to actually claim back my ticket if I'm not crashed or something, because actually there are economic incentives to produce a block if you are a block producer. But this is a known problem because actually there's no solution. This protocol end goal is to hide who is the next block author. So if it doesn't claim back his slot, we cannot punish it at all. And it's a problem with all the other protocols as well. So a word about the implementation status of Sassafras. Sassafras has been one of the focus activities of the SDK node, part of the SDK node team for 2022. We at least strive for a solid production-grade implementation for at least for the end of the first quarter of 2023. I mean, the structure is already there. We have to actually improve some parts and properly integrate the zero-knowledge part that is not integrated yet, and stuff like that. But the structure is already there, and we are testing it. And also, we are going to start an RFC process to better define the protocol in a more engineering-friendly jargon, because the protocol is actually defined by a research paper, and this RFC process will allow the community at least to have their implementation, or at least incentivize third-party implementers to participate and stuff like that, at least to follow the best practices in the engineering. And yeah, the implementation status can be followed on GitHub. There's a main open tracking issue with this tracking number, and there's also a main PR where all the work that we are doing is actually flowing into. And yeah, that's it for Sassafras and status. Thank you. If there is any question? No questions?
No
Good.
questions? So if you
Yeah, one question.
I'm going to ask this. Please don't.
Hello. Oh, hi.
Hi.
With Sassafras, if the block producer doesn't claim their block, right? You mentioned that that's a point where the chain can halt. That's right.
I cannot hear you. Sorry. Okay.
If a block producer or a validator doesn't claim their slot, You mentioned I mean, what's the fallback to prevent against just a chain halt that just...
It will be just a slot that is just skipped.
Right, so the other block producers will...
The next slot will be claimed by the proper authority, and the status of the chain will actually progress. What can happen is that there is a delay or a network split where in one history, the authority claimed that slot, and in one history not.
Right.
So in the end, it works like all the other authoring consensus protocols, where usually the longer chain wins, even if it doesn't contain the author of that slot. Maybe the one that doesn't contain the claim for that author will be longer anyway, so it will win.
Right, gotcha. So essentially like a timeout, like a time period that you have to claim that slot, and if it's not made, then it just gets skipped.
Yeah.
Right, cool. Thank you.
Yeah. Another question.
Hold on.
Hey. So you made this general point about preferring availability over safety, right? So my question is the following. So suppose the finality gadget gets stuck on a, let's say, short fork, and then the, let's say, Babe or Sassafras or Aura will continue growing on one of the forks, right? So what's the value in this if it's still possible that Grandpa will finally finalize the shorter fork? So what's the benefit of growing this one of them?
Okay, when an author is going to decide what is the best chain to actually grow, to actually produce the next block, we'll always choose the one containing the last finalized block. It will be an error to actually, if you decide because of your choice to produce the next block over a branch containing not the finalized block, it will be just ignored by all the other participants in the network because it's not following the protocol properly.